All right. So the last kind of way to think about indeterminate forms, or the last way we're going to look at indeterminate forms, are indeterminate forms of this variety: 1 to the infinity, 0 to the infinity, and infinity to the 0. Now, each one of these we're going to treat in the exact same way, okay? So I'm going to work 2 examples. So first things first, let's look at which form we have here. So as x approaches infinity, we have infinity raised to the 1 over infinity, which is 0. So this is an example of the infinity to the 0 case. Now again, every one of these 3 forms is going to be worked the same way, okay? So what we're going to do is we're actually going to do a little bit of messing around with this, okay? So to start with, I'm just going to take this function, x to the 1 over x, and I'm going to take a natural log of it. Now the whole reason we did this is the same reason we do this when we're doing logarithmic differentiation, is by our logarithmic rules that allows that 1 over x to come out in front. Okay, so I've changed this ln of x to the 1 over x to 1 over x times ln of x. Now notice that I am fundamentally changing my function here. Okay, so I am now taking a different limit. I'm not taking this limit anymore. I'm going to take the limit as x approaches infinity of this ln of x to the 1 over x, which is really the limit as x approaches infinity of 1 over x ln of x. This is a different function than what I started with, but we're going to deal with that at the very end. Okay, now let's look at what form we have here. As x goes to infinity, 1 over x goes to 0. As x goes to infinity, the natural log of x goes to infinity. So technically, if I think of those as 2 distinct functions, I have 0 times infinity, which isn't really ready to apply L'Hopital's rule. But again, I can do something a little bit sneaky and say, well, 1 over x times natural log of x is really the limit as x approaches infinity, natural log of x over x. These say exactly the same thing. And now if I think about my form, as x approaches infinity, natural log of x goes to infinity, x goes to infinity, so I have the form infinity over infinity, which means I'm ready to apply L'Hopital's rule. So we're going to apply L'Hopital's rule. Okay, L'Hopital's rule says I'm going to take the limit of the numerator, which is 1 over x, times the limit of the denominator, which is just 1. That's pretty handy. Now I have the limit as x goes to infinity of 1 over x, but here I can directly substitute. As x goes to infinity, 1 over infinity is 0. So this limit is 0. Now here's the thing that you need to remember. This was not actually the limit that I wanted. This says that the limit as x approaches infinity of the natural log of x to the 1 over x equals 0. I took a natural log of this function to begin with, and so what I really need to do is undo taking that natural log. But to undo taking the natural log, that means doing e raised to that. The exponential and the logarithmic function, the natural logarithmic function, are inverses. Okay, so my final answer, right, basically says, hey, raise both sides of this equation to the e, or take e raised to both sides of this equation. And basically, with a little bit of hand waving, since e is a continuous function, we can move it inside of the limit. These 2 cancel, and I'm left with what we wanted. So this literally says that the limit as x approaches infinity of x to the 1 over x is going to be e to the 0, but e to the 0 is 1. So this limit equals 1. Okay. Another way to think about this is if we took a natural log at the beginning of the problem, to undo that, we have to do the exponential at the end. So our final answer is going to be e raised to whatever we got. All right, let's try that same method with our bottom problem here. All right, so first thing we're going to do is we're going to figure out what form we have, which of our 3 indeterminate forms we're dealing with. Okay, well, when I plug in infinity, 1 over x goes to 0. So I have 1 raised to the infinity. So we're in this form. 1 to the infinity. Now again, remember this method is going to work exactly the same. What I'm going to do is take a natural log of my original function, the thing that I'm trying to find the limit of. By the power rule for logarithms, I'm able to then move that x out in front. Okay, this is actually the function I'm going to work with. Notice that that is fundamentally different than the function that I started with because I took a natural log. So when I'm done, at the end of this process, I'm going to have to do the exponential to kind of undo that process. Okay? All right, so I'm going to not work with my original function. I'm going to take the limit as x approaches infinity of this, the natural log of my function. All right. Okay. Well, now let's check what form we have, given this new limit. Well, as x goes to infinity, x certainly goes to infinity. As x goes to infinity, 1 over x goes to 0. So I'll have natural log of 1, but natural log of 1 is 0. So we're in that 0 times infinity form. So we're going to perform a small change. I'm going to take this x, and I'm going to move it into the denominator. I'm going to take the limit as x approaches infinity of ln of 1 plus 1 over x over. When that x moves to the denominator, he ends up with a negative exponent. So these are exactly the same. Let's see what form we have now. ln of 1 plus 1 over x as x approaches infinity is still 0. X to the negative 1 as x approaches infinity is also 0. So now we've changed this to the form 0 over 0, which is one of our standard L'Hopital's forms. So we can directly apply L'Hopital's rule. All right. So L'Hopital's rule says, I'm going to take the derivative of the top, the derivative of the bottom. Derivative of the top is going to be kind of fun. Derivative of the top is going to be a chain rule problem because I have to do the derivative of the natural log of 1 plus 1 over x. Chain rule says I do the derivative of the outside, which is 1 over x. I'm going to leave that inside alone, times the derivative of the inside. Well, the derivative of the inside, 1 plus 1 over x. The derivative of 1 is 0. The derivative of 1 over x is negative x to the negative 2. Okay, super. Now on the bottom, I have x to the negative 1. I'm going to take the derivative of that. The derivative of that is negative x to the negative 2. Now notice what's really, really handy with that. We've applied L'Hopital's rule. Look at that. Those two things cancel so beautifully. And we're left with the limit as x approaches infinity of 1 over 1 plus 1 over x. But this we can directly substitute in. When x goes to infinity, this term goes to 0, leaving me with 1 over 1, or a limit of 1. So again, that means the limit as x goes to infinity of the natural log of 1 plus 1 over x to the x is 1. But that wasn't what we wanted. Okay, what we wanted was just 1 plus 1 over x to the x. So to finish that problem, I'm going to take this, and I'm going to do e raised to that answer because it's going to undo that natural log that we did in the beginning. But e to the first is just e. So this limit equals e. All right, so that's our last kind of indeterminate form. We didn't do a specific example of 0 to the 0, but it would work exactly the same way. We would take the natural log to pull the exponent out in front. That would give us some type of form infinity times 0. We would then switch that to get our traditional L'Hopital's form, 0 over 0 or infinity over infinity. Apply L'Hopital's rule, and then at the very end, remember that whatever result we get is really the natural log of what we want. So we're going to raise it to the e to get our final answer.